purpose of today's lesson is to recognize, identify, and graph solutions to two-variable inequalities and apply these to real-life scenarios. To do this, let's go back to the problem we did yesterday with the Coney Island amusement park, where we came up with the scenarios that if you had a $50 budget, what were the combinations of rides and games you can go on. So if we go back and graph that for a moment, where our x-axis was rides and our y-axis was games. Again, we're doing exactly what we did yesterday. We came up with 6 different scenarios of a combination of rides and games we can go on. So just give me a moment to label these axes. And again, I went anywhere from 10 games and no rides to 5 rides and no games. And then I can even plot the points in between just to make it a little bit more accurate. And there we go. You'll notice that there are no arrows because I can't go beyond my $50 budget. Now what we want to do is say to ourselves, well, my parents gave me $50, but I don't have to spend all $50. Okay, they didn't say, here's $50, come home with nothing. So what are some possible scenarios where you would spend less than $50? So for example, 2 rides and 5 games, 3 rides, 3 games, 1 ride, 6 games, 4 rides, 0 games, 3 rides, 2 games, 0 rides, 9 games, and finally 2 rides and 4 games. Now there's other scenarios that you can have here. These are just the 6 of them that I chose. Now if you were to go back and plot all of those points, so for example 3, 3, which is here, 1, 6, which is here, 4, 0, here, 3, 2, there, 0, 9, there, and 2, 4, there. Over 1. And as my line disappears a little, sorry about that. Hopefully you'll notice, which is what the next question prompts you. What do you notice about all of those points that we just graphed? Or if you had different ones, what do you notice about them? And hopefully you'll notice that all of these points are below to the left of the original line. Now, you might recall that yesterday we wrote the equation for this as 10x plus 5y equals 50. Now, how would that change based upon the fact that you don't have to spend exactly $50? Well, you should recognize that as an inequality. And so what is it that you can do? I can spend anywhere from $50 or up to $50 or less. So how would I write that as an inequality? 10x plus 5y is less than or equal to 50. Now, let's go so that we understand exactly how we would graph inequalities. Let's start by graphing an equality. The equality is y equals 2/3 x minus 4. You've learned how to graph these. It's in slope-intercept form. You graph the y-intercept of -4. You use the slope of 2/3 to go up, rise 2 to the right 1, or left down 2 to the left 3. I'm sorry, it was up 2 to the right 3. Okay? I draw my line, I draw my arrows, and I'm good. Now I want to draw this in the context of an inequality. Well, those same 3 points are going to exist. If you recall, I have an equal sign under this inequality. That's going to tell me, like my filled in circle that it's part of the solution set. But now it's a less than. Like the inequality we saw in the do now, less than our solution set were points below this line. So we are going to shade in that area because those points below the line are part of the solution set. Now, how can we check that? Well, a simple way to check it is to choose a point that's in the solution set. So let's say I chose the point 3, negative 5. Negative 5 is my y value. 3 is my x value. So when I solve this, 2/3 times 3 is 2. Is this a true statement? Yes. Then that means all of these points in this shaded blue area and below onto infinity are part of my solution set. Now I go to the next one. Again, the same 3 points are going to show up. However, now it doesn't have an equal to sign. So like my open circle on a number line, I'm going to do dashed lines. Is my shading going to be any different? No, it's still less than. Only difference, solid line, the points on that line are part of the solution set. Dashed line, the points on that line are not part of the solution set. Let's go to the next example. Once again, same 3 coordinates I'm going to start with. It's got an equal to, solid line. But now it's greater than, so I'm going to shade in the area above. Next example, again, sorry to belabor doing the same 3 points, but it just makes that part easy. Now instead, because it's no equal to, a dotted line, shading is still the same. Okay? So, to recap the concept, what we're going to do is solve for solve for y, so that it's in y less than or equal to or greater than or equal to, whatever it is, mx plus b. Okay? Step 2, graph the line. If it's less than or greater than, we make a dotted or dashed line. If we have the equal to sign underneath, we make a solid line. For less than or equal to, we're going to shade below the line. And for greater than or equal to, we shade above the line. Okay? If you keep in mind that we are doing our graphing, or we are graphing the same way as we would be graphing a line, that will make life easier. All we are differentiating is solid versus dotted and a shading concept. So let's take a look at the next examples. These are already set up for me in y isolated form. I plot my y-intercept of -3. My slope is 2 or 2 over 1. I go up 2 to the right 1, down 2 to the left 1. Since it's just greater than, it's a dotted line. And since it's greater than, I'm going to shade above. Second one, same y-intercept. However, the slope is a -2 over 1, so I'm going in the opposite direction. Still a dotted line. It's greater than, so I'm shading above. Okay. Going on to the next. What I would like to do is get these into y equals or y is less than or equal to form. That way I know which way to properly shade. So I get the inequality y is less than or equal to -2/3 x plus 2. I graph my plus 2. I go up 2 to the left 3, or down 2 to the right 3. It's got an equal to sign, so I'm going to use a solid line. It's less than, so I'm going to shade below. And then finally, I subtract. Now you've got to be careful because as we've done before, if you multiply or divide by a negative, your inequality flips. In addition, double negative, one in the numerator, one in the denominator, makes it a positive. There's my intercept, up 3, right 4, down 3, left 4. It's a dotted line, and I'm going to shade above. Now, someone in one of the classes graphed this by finding the y-intercept and the x-intercept and didn't convert it into y equals form. That is okay. The only problem is it doesn't tell you which way to shade until you have it y by itself. A suggestion is 0, 0. Plug in 0 for x and 0 for y and solve. If this is a true statement, which it is, that means 0, 0 is in the solution set, and then that tells you which way you can shade. Okay? Finally, a couple of special situations. Let's say I have the line, y, or the equation y equals -2. How would you graph that? Well, hopefully you recall that when you have only one variable in your equation and are asked to graph it, they are special scenarios. How do I graph this? Well, where is y -2? Here. What kind of line am I going to draw? A horizontal line. Why do I do that? Because every point on this line is some number x and -2. Contrast that with x equals 5. I go to 5 on the x-axis and I draw a vertical line. Why is that the case? Because every number on this line is 5, comma, y. Now, how do I do that with an inequality? Well, I'm going to go to the same point, -2. It's got the equal sign there, so it's going to be solid. And then it says greater than or equal to. I'm going to shade above. Every y value above this line is greater than -2. And then finally, x is less than 5. Since there's no equal sign, it's dashed. Since it's less than, I shade to the left. Every x value to the left is less than 5. So to summarize, when graphing inequalities, you're going to graph or identify coordinates just like you would if it were an equation using your slope and y-intercept. You're going to determine if it's a solid or dotted line based upon whether it has the equal to or not sign underneath the inequality. And then you're going to determine the shade based upon if it's greater than or less than inequality.